Hi everyone, in this video we'll be looking at section 7.1, which is the area between two curves. So first we're going to look at the area of a region bounded by two curves. So remember the integral from a to b of f of x dx right here represents the area underneath the graph of f of x from x equals a to x equals to b. So we remember that from Calc 1. So now suppose we have f of x and g of x. They're two continuous functions, right? Continuous basically just means I can draw them without picking up my pencil, such that f of x is greater than or equal to g of x on the whole interval from a to b. So let's look at what that means, f of x being greater than g of x on the interval. So if I had this graph here, and say I have this red function here. This is f of x. Now, if f of x is greater than or equal to g of x on this whole interval, then that means that f of x lies above g of x. All right? And we should probably put, remember this is on the interval from a to b, so let's put our interval down on the bottom on the x-axis here. So now the question is, how do we find the area A that's bounded by the graphs of f of x and g of x on the interval from a to b? So let's first draw what this area bounded by the graph looks like, right? Bounded by f of x and g of x. So let's see how big we'll make this. This is the area we're trying to find, right? This is that area A that's bound by the graphs of f of x and g of x. All right, so this is the area A. So how do we find that? Well, we know that the integral, so basically one way to think about it is we could find the total area that's under f of x, and then if we subtract the area, right, the total area that's under f of x is all of this, right? The total area that's under g of x is just this piece. So if I want just the orange piece there, what I can do is I can say, okay, well, the total area, the orange piece, is going to be the area under f of x minus the area under g of x, right? And then by definition, we know that the area under f of x is the integral of f of x from a to b minus the integral from a to b of g of x. And then remember that by rules of integrals, since the limits of integration are the same, I can combine f of x minus g of x in the same integral as follows. Right? Instead of writing this as two integrals, I can write this the integral of f of x minus g of x dx. Right? So what did we just find out? We just find out that if I want to find the area of a region between two curves, right? If f of x is a continuous function and g of x is a continuous function on the interval from a to b, such that f of x is greater than or equal to g of x, right? This whole piece right here just means f of x on top of g of x, then the area bounded by the graphs of f of x and g of x is exactly that formula we just found, right? The integral from a to b of f of x minus g of x dx. Another way I like to think about this is the integral from a to b. This is a little bit more informal, but it's really just always going to be the top function minus the bottom function, right? So in other words, if I want to find, if the question asks, like the next example 1 will ask us, if I want to find the area bounded by two curves, what do? I need to graph those curves and see which one's the top and which one's the bottom, and then I just take the integral from the beginning to the end of the top function minus the bottom function. All right, so let's look at this example. Let's look at example 1 here. I guess I can leave our formula up here. Okay, so find the area bounded by the graphs of y equals x squared plus 2, y equals negative x equals to 0, and x equals to 1. So first we should always sketch the graph. All right, so let's sketch the graph of f of x. Remember that x equals to 0 is the y-axis. right? Because that's a vertical line at the x value 0, which is a y-axis, right? And this is a vertical line here at x equals to 1, right? That's what x equals to 1 means. Okay, so first let's look at x squared plus 2, right? So x squared plus 2, remember this is a parabola, a parabola, x squared, and the plus 2 means we shifted up 2 units, right? So this looks something like, this, right? Y equals x squared plus 2, right? Shifted up 2 units. So now let's do the graph of y equals negative x. Well, y equals negative x is a line with slope -1 and y-intercept 0, right? So that looks like this function right here. This is y equals negative x. So we already said that the other line is the y-axis. We're going to bound it by the y-axis, and we're also going to bound it by the line x equals to 1. So x equals to 1 is this line right here. So let's go ahead and sketch what our area that we're trying to find is. Our area that we're trying to find here is this piece. All right, this is the area that's bounded by all of those graphs. Okay, so let's figure out where are the A and B values, right? Where we start and finish. So we start at right here, right? So we start at, what's that x value? That x value is x equals to 0. And go to, where do we end? We end right here, right? And that's x equals to 1. So what does that mean? That means our A equals to 0, where we start, our first limit of integration, and our B equals to 1. That's where we end. So now what I always like to do in these problems is identify the top function and the bottom function, right? Because that's what our formula is. So our top function on this interval, which function's on top of this area? Well, the top function, let's get rid of some of these arrows here. Whoops. Sorry, I'm still getting used to the iPad. So let's do this. Our top function, again, is going to be the x squared plus 2 function. Because it is on top, it's the upper bound of that area, that orange area, right? So now, what's our bottom function? Our bottom function is what's our lower bound, and it is that function negative x, right? So now that we know our top function, our bottom function, we know our start and finish, we know our A and a B, now we use our formula, right? The area is always going to be the integral from A to B of the top function minus the bottom function, d of x. Notice here, that negative sign, I'm subtracting an entire equation, right? I'm sorry, an entire function. So we need to always make sure to distribute negative sign. So I'll try to be careful in our notes here to write out that step so that we don't forget. Okay, so what is our A and B? We said our A was 0, our B is 1, because that's where we start and finish x values. Now our top function here is x squared plus 2. Our bottom function is negative x, so I subtract negative x. Again, careful with your negative signs, dx. Now that's the integral from 0 to 1 of x squared plus x plus 2. I'm just writing that in descending powers of x, right? Now we perform our definite integral. So here I would get 1/3 x cubed. When I do my antiderivative of x squared, here I would do 1/2 x squared, and here I would do 2x, and I'm going to evaluate that from 0 to 1. And since we're already familiar with evaluating integrals, I will just tell you that that final answer is going to be 17/6. I'll let you compute that in your spare time to verify. Okay, so notice in this last example that x squared plus 2, the purple function, and y equals negative x, the blue function, did not intersect. So what happens when they do intersect, right? So if two functions intersect on the interval and we're interested in finding the area bounded by them, we have to be more careful. The points where they intersect, they'll either determine those endpoints x equals a and x equals to b. So an example of that would be if I had a function that looked like so. If I had, say, f of x was this function, and we should probably continue that like this, and say g of x was this function. Right? So in this case, those points where it intersects right here, that would determine, if I asked you the question, hey, what's the area bounded by f of x and g of x? Well, the area bounded by f of x and g of x would be this area right here, and the starting point and ending point for finding this integral would be those points of intersection, those red dots, right? The other thing that can happen is that they can cut the interval into subintervals. So let's look at another example here. If I had this graph like this, and say my f of x looks something like, let's look something like this, right? Say this was my f of x, right? And then I had another function, say this function right here, that was my g of x. And I ask you to find the area bounded by these two curves. Well, if you notice, if I ask you to find the area bounded by these two curves, right, this is part of the area bounded by those two curves, but also this is part of the area bounded by those two curves, right? And so these intersection points here, we have 3 of them. Notice on this first piece of let me highlight it here. Let's get a different color. On this first piece of the interval, my blue function is the top function and my purple function is the bottom function. But on the second piece of interval, like from here to here, the purple graph is the top function and the blue graph is the bottom function, right? So what this does, what these intersection points do, is they break the x-axis, break the domain into multiple subintervals, and then on each one of those subintervals, I need to figure out which one's the top function, which one's the bottom function, right? So we have a nice step-by-step process for finding the area bounded by two intersecting curves. The first thing we need to do, most important, is to find all points of intersection. Right? How do I do that? How do I find these points of intersection? Those red dots, I set functions equal to each other and solve for either x or y, depending on if we're integrating with respect to x or y. And we'll look at an example where we integrate with respect to both. Okay, so the next thing we do, once we figure out the points of intersection, we need to check which curve is above the other on each sub-interval, right? So for example, on this graph on the right, again, on this little piece of it, the blue graph's on top, and then on this little piece of it, the purple graph's on top, right? And then what we do, we use the area formula from before on each subinterval. Whoops, that's really messy. Sorry, guys. Right, so for example, for this piece of graph, we would have the blue functions, the top function, so we'd go from the first intersecting point to the second intersecting point. The blue function would be the top, the purple function would be on the bottom, and then the second piece, it would be a different integral that we would add to it, and we would say, okay, the integral from the second intersecting point to the third intersecting point with the purple function on top and the blue function on the bottom. Okay, so that is our step-by-step process. Now let's illustrate that. So let's find the area of the region bounded by the graphs of f of x equals 2 minus x squared and g of x equals x. So again, first step here, what we want to do is we want to graph these functions. All right, so here we've got this. And now let's do the graph of negative x first, just because I know it's going to make it easier to draw. So the graph, of g of x equals x, right? So that's a line with slope 1 and y-intercept 0. So that's this line right here, right? That's the graph of g of x equals x. And now let's do the graph of 2 minus x squared. Well, the minus sign means I flipped the x squared, the parabola, upside down, and the 2 means I shifted up 2. So this is going to be an upside down parabola shifted up 2. All right, so it looks like this. So this is f of x equals to 2 minus x squared. So the area that we're trying to find that's bounded by these two graphs is this area right here. So notice that in this graph and this question, they don't tell us where we start and finish, right? But we can figure out where we start and finish, right? The area that's bounded is going to be these intersecting points, right? This point, this x value here is going to be my A, and this x value B is going to be, this x value here is going to be my B. So the first thing we need to do is find the points of intersection. So again, the way we're going to do that is we're going to set f of x equal to g of x. So I'm going to set 2 minus x squared equal to x. So I hate to deal with negative coefficients with negative coefficients with the leading power of x. So I'm actually going to add x squared and subtract 2. So here I get 0 is equal to x squared plus x minus 2. So now this is a quadratic that I need to factor. Two numbers that multiply to equal to negative 2 but add to equal to positive 1. How about x plus 2, x minus 1? So I have x equals to negative 2 and x equals to 1. So this a value here is negative 2. And this b value here is positive 1. All right, so we know where we start and finish. And now we need to talk about which function is going to be the top and bottom. So my top function is going to be the one that's on top. Again, it's the purple function. All right, so my top function is 2 minus x squared. And my bottom function, again, it's the one that's on bottom, right? And it's going to be the x function, right? So now my area, again, as always, is going to be the integral from a to b of top minus bottom dx. Our a to b, we know we start at negative 2. We go to 1. We solve for those. And now it's going to be my top function, which is 2 minus x squared, minus my bottom function, which is just x. So now we integrate this, right? I get 2x, minus 1/3 x cubed minus 1/2 x squared. Evaluate that from negative 2 to 1. Again, I'll let you do that in your free time, but that ends up being 9/2. Okay, so now let's look at a more interesting example, right? This is going to be one where our graph intersects multiple times, and that will break our domain into pieces. So this, we look at the graphs. We want to find the area bounded by f of x equals 3x cubed minus x squared minus 10x, and g of x equals negative x squared plus 2x. So in this course, you'll be allowed to use a graphing calculator, and that will be helpful to graph a function like this, right? These aren't easy transformation graphs like we were able to graph earlier in the notes. So I have this convenient app which you can download on your smartphone as well. It's called Desmos, and it allows you to graph any function. You can graph multiple functions, right? You just type them in here with the keyboard. I already have our two functions up, right? So the black function is the 3x cubed minus x squared minus 10x, and the red function is our negative x squared plus 2x. Right, so this is what our graph looks like. So we're going to go ahead and try to sketch this graph. So first I'm going to draw the quadratic function. Whoops. So graph this right here. So the quadratic function, again, this is just a sketch so we get an idea of what's going on and for your notes. So that's going to look something like this, right? This is the g of x, right? The negative x squared plus 2x. And then now let's try to draw the other function, right? So it looks like it goes up and down. So it goes something, whoops, and I think it goes through the origin, right? So this goes like this, zoop, and zoop, something like that. Again, this isn't a perfect graph, but you get the idea of what's going on. We get the important pieces, right? We get the origin, something's going on at the origin, something's going on at 2, and then down here in the bottom left, it also crosses. Right? So again, let's mark our intersection points, right? Here's our intersection point, here's our intersection point, here's our intersection point. And let's go ahead and color what our area that we're trying to find is, right? This would be the area that's bounded by the graph. This would be area that's bounded by the graph. And again, nothing down here, right? Because down there it's not bounded, both sides go on forever. And nothing over here, again, because both sides go on forever, it's not bounded, right? So we have two distinct pieces of the graph, right? We have like this piece that's going to have the blue function on top and this piece that's going to have the red function on top, right? So first let's find those points of intersection. So again, looking at the graph on our graphing calculator here, it looks like it's going to be 0 and 2, and then down here maybe negative 2, right? But let's go ahead and verify that. We should always verify it because with a graphing calculator, we're not exactly sure. So 3x cubed minus x squared minus 10x, and I'm going to set that equal to negative x squared plus 2x. Let's add x squared. Let's subtract 2x. So I get 3x squared minus 12x equals to 0. In order to solve this, whoops, that should be a cube, shouldn't it? In order to solve this, I need to factor out a 3x. So I'm left with x squared minus 4. X squared minus 4 factors, it's a difference of squares, right? So it factors as x plus 2, x minus 2. So I get x equals to 0. X equals to negative 2, and x equals to 2, just like it looked like. So this is negative 2, this is 0, and this is 2. So again, I'm by the line green there, I have two pieces of the interval, and I'm going to have two different integrals from some, depending on which one's the top and on the bottom. So on the interval, oops. The first interval goes from negative 2 to 0. Which function is the top function? Well, the top function is going to be the blue function. The blue function is f of x, which is 3x cubed minus x squared minus 10x. And my bottom function is going to be the purple function, which is the minus x squared plus 2x. On the interval, the other interval, which is from 0 to 2, my top function is going to be on that interval from 0 to 2, it's going to be g of x, which is the negative x squared plus 2x, and my bottom function is going to be the blue function, which is 3x cubed minus x squared minus 10x. So again, to find this area, I'm going to do the integral of the top minus bottom for the first piece, and then I want to add that other piece of area, right? This is like, well, actually, let me try doing this. Might make it a little bit easier to realize what's going on. This is like A1, a first piece of area, and this is like A2, a second piece of area. So my total area is going to be those two areas added up, right? So again, the first one just by our formula, is going to be top minus bottom on that first piece, plus the second, which again is going to be top minus bottom dx, right? So again, that first piece, I'm going to go from -2 to 0. My top function is going to be 3x cubed minus x squared minus 10x. I'm going to subtract my bottom function. I'm doing careful minus parentheses so I remember to distribute that negative sign. And then I'm going to have to go down a little bit. But now I do my other function, or my other area, which is going to go from 0 to 2. And again, my top function is going to be the minus x squared plus 2x minus parenthesis 3x cubed minus x squared minus 10x. Whoops, need a bracket. Dx. So this is going to be the integral from -2 to 0. Again, I'm distributing this negative sign, so I'm going to, I'll get 3x cubed. I get minus x squared plus x squared, so the x squareds are going to cancel out. And I got minus 10x minus 2x, so minus 12x dx, minus the integral from 0 to 2 of, I'm going to write this in descending order of powers of x. I would get, again, if I distribute the negative sign, negative 3x cubed. Then I got a minus x squared and a plus x squared when I distribute the negative sign, so those cancel out. And then I get a plus 10x plus 2x, so plus 12x dx. And if you need to take the time to distribute that out and see that I got the right answer, take your time. Do that workout on your own. Now what we get is we get 3/4 x to the fourth minus 6x squared evaluated from -2 to 0 minus -3/4 x to the fourth plus 6x squared, and that one's going to be evaluated from 0 to 2. And if I do that, my final answer will be 12 plus 12, which is 24. Again, I'm not doing those definite integrals because that's more of a Calc 2 thing. Or I'm sorry, Calc 1 thing. Okay, so in the graph of a function, when the graph of a function, try that again. When the graph of a function of y is a boundary of a region, it is often convenient to find the area by integrating with respect to y, right? So in other words, if all these functions I'd said f of x equals x squared plus something, 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 right? Sometimes a function can be given in terms of y, like in example 4 here, x equals 3 minus y squared and x equals y plus 1. So in this case, it's not necessarily convenient to convert everything in terms of y equals something, something, something. It's actually more convenient to just keep everything in terms of y and integrate, right? So when I do that, when I integrate with respect to y, I always think about it as turn my paper over sideways. And if I turn my paper over sideways, then I still get the top and bottom thing. But if I don't, then this area ends up being, instead of top and bottom when it's in terms of x, it ends up being like my right function minus my left function. And I know this sounds a little bit awkward, but in this next example, I'll try to help explain a little bit more here. Okay, so find the area of the region bounded by the graphs of x equals y, 3 minus y squared and x equals to y plus 1. So first let's practice graphing these, right? So x equals 3 minus y squared. In order to graph these the way we're comfortable with, I still convert these to y equals something in graph, right? So if I did this, I would end up getting, if I solve for y, I get y is equal to plus or minus, because of the square root, and again, this is why it's awkward, plus or minus the square root of x, minus x plus 3, which is y equals plus or minus the square root of minus x minus 3, right? So what does this look like? Well, the square root function, remember, looks like oops, that's still going. The square root function looks like this, but that's not what we want here. We want this right here means that it is reflected over the y-axis, right? So our graph is actually going to look not like that, but like this. And then this piece right here means that we are going to shift to the right 3 units. So our graph actually ends up reflecting over the y-axis, shifted to the right 3 units. So this is actually that top piece. That's the plus part here. The minus part, remember, means we reflect it over the x-axis. So we actually need this piece too. All right, so again, it's a little bit awkward, but that's how we get this graph of this graph here, which is x equals 3 minus y squared. So now the other one is a little bit easier, right? It's x equals to y plus 1, so that just means y equals to x minus 1. And again, that's just a graph of slope 1, y-intercept negative 1. So that looks like this graph right here. So this is y equals x minus 1. So this is going to be an intersecting point, and this is going to be an intersecting point. Oops, and I should write this in terms of the x function. So x equals to, x equals to y plus 1. Okay, so now I am going to tell you the easiest way to think about doing this is turn your paper on its side. So that way you're staring at the graph, and this is the bottom of the graph, and this is the top of the graph. So this is the top, and this is the bottom. Because if you do it this way, you're going to integrate in terms of y. So this is going to be your start. I'm sorry, this is going to be your start because it's the smallest. Because again, if we think about if this was in y, this is going to be my start, y, and this is going to be my end, y. Because that's the lowest y value and that's the highest y value. So my start, remember, is the lowest y value, and my end is going to be the highest y value. Got a continuous axis here, it's driving me crazy. Okay, so we need to find those intersection points. And again, we want to find them in terms of y. We're going to leave everything in terms of y here. So I need to find those points of intersection in terms of y. So I set 3 minus y squared equal to y plus 1. So add y squared minus 3. So I get 0 is equal to y squared plus y minus 2. Again, this is just two numbers that multiply equal to negative 2, add to equal to positive 1. So y plus 2, y minus 1. So 0 is equal to y plus 2, or whoops. Y is equal to negative 2, and y is equal to 1. All right, so this y value here is negative 2, and this y value up here is positive 1. All right, so we can think about this again in two ways. We can flip our paper over, and if we flip our paper over, again, like I said, top being top, bottom being bottom, then the top function is the purple function, and the bottom function is the blue function. Right, so before I write area, let's write top and bottom, if we think about it that way. So my top function here is going to be the purple function, 3 minus y squared, and the bottom function is going to be the y plus 1. Now, if you're not comfortable with that, again, this formula up here that I wrote down and starred, I can think about this in terms of right and left. Now that, whoops, and this should have been in dy, because this is when things are in terms of y. So if I'm looking at this function, I'm going to start again at this y value negative 2, go up to the y value 1, and I do right and left function. The right function, the far right function, is again the 3 minus y squared. So again, this is still my right function, and this is going to be my left function. So it's the same formula here because right is the one just like top, the first one, and left just like bottom is the second one. So my area here is going to be the integral from a to b, and I'll just go ahead and write top slash right minus the bottom slash the left, depending on how you think about this problem. And again, either one is fine by me. And I put dy just because, remember, everything's in terms of y here. So again, my starting y value, that's probably the biggest issue when we start to integrate with respect to y, is people still try to put the x value here and the x value there. No, we don't want x values. Everything's in terms of y. So my starting y value we found to be -2, and my ending y value we found to be 1. And now we do our top or our right function, which is 3 minus y squared. And then we subtract our bottom or our left function, which is y plus 1, dy. It's the integral from -2 to 1 of -y squared minus y. And then if I subtract, again, we distribute this negative sign. 3 minus 1 gives me 2, dy. Just because everything's in terms of y now, we still integrate like normal, right? Y is just the variable. So now I integrate this. I do 1/3 y cubed minus 1/2 y squared plus 2y evaluated from -2 to 1. And if I do that, I get 9/2, which is our final answer. Okay, and here at the bottom, I put some relevant textbook exercises. You have your homework to go through many of these problems, but if you have extra time and want extra help, here's some relevant textbook exercises for you.